What's up, CoderByte? Welcome back to another video series on data structures and algorithms. I'm Elizabeth, I'm new here, but I'm super excited to be joining the CoderByte YouTube team. If you haven't already, subscribe to our channel so you can stay up to date on all of our latest and greatest content. We have a bunch of new videos coming down the pipeline, so be sure to keep your eyes peeled. Today, we'll be kicking off our graphs course. I'll be giving an introduction to the data structure along with some relevant terminology. We'll also live code some implementation examples to set us up for success when it comes time to talk about traversals and actual interview problems, which will be coming in the next few videos. So, what exactly will we cover in this video? First, we'll define the term graph. We'll learn some key terms such as vertices and edges. We'll then do a live implementation example of the graph data structure and code. We'll actually give 3 different examples for how you can implement the data structure and code. I'll be coding in JavaScript, but if anybody in the audience wants to do this alongside me in Python or some other language and leave it in the comments below, we'd love to see what you guys come up with. We're also going to talk about some terminology surrounding graphs, directed versus undirected graphs, weighted versus unweighted graphs, cyclic versus acyclic graphs. The real core of this video will be the implementation examples. However, this will really set us up for next video when we talk about different kinds of traversals, and of course the following videos where we'll talk about real actual interview questions. So graphs, what are they? This is kind of one of those data structures that I always think of when I think of an interview problem. You know that meme where it's like what you think you do, what your friends think you do, what your mom thinks you do, what you actually do. So whenever I think of an interview problem, I'm always like, graphs, how do you get from point A to point B in the shortest possible time? I don't know if anyone else shares that. But of course, here's a meme. Here's a great meme. So what is a graph? It's actually relatively simple. A graph is just a data structure with nodes or vertices and edges or the connections between the nodes. Typically, a visualization of a graph will be of nodes as circles with their values inside them and the edges or connections between them represented by lines. I think we've all seen something similar to this. The nodes here would be 1, 2, 3, 4, 5, and 6, indicated by the circles, and the connections between them being the lines. So as you can see, between nodes 1 and 2, there's a connection, and 1 and 5, but there's no direct connection between nodes 1 and 4. So if you've seen our videos on trees or you know anything about trees, you might be asking yourselves, Elizabeth, that sounds a lot like a tree. So what's the difference? There isn't. A tree is really just a special kind of graph with a couple different parameters that must be true for something to be a tree versus just a regular old graph. So trees are just a special kind of graph, except that they can only have one root and one unique path between any 2 nodes. A graph can obviously go beyond that and have any number of root elements and multiple paths between 2 nodes. So as you can see in this example, the tree in our left, there's only one way to get from node A to node H, and that's through nodes B and nodes E, right? A, B, E, H. However, in the graph on the right, if you're trying to get from node A to G, there are different paths that you could take. You could go through nodes E and F, or you can go through nodes H, and both are valid paths. So that is what, the main difference is between a tree and a graph. So this is a relatively simple concept, right? Nodes and the connections between them. How can we represent this in code? So it turns out there are a few different ways to represent this in code, and mostly we'll talk about why you would need to represent graphs differently based on the time complexity and space complexity of the algorithms. If you haven't seen our great course on big O notation or time complexity and space complexity, I'll link that below. But that's most of the time what we're going to use to determine which kind of representation we're going to choose when it comes down to representing the graph in code. So let's get into it. The first kind of representation that we're going to talk about is two different lists. It's a list of the vertices. Remember, vertex is just a fancy word of saying node, and a list of the edges or the connections between the nodes. So let's take a look at what that will look like. So as you can see, here's a graph, has 5 nodes, A, B, C, D, and E, and there are some connections between them. And here is how we might represent that in JavaScript. So we have a list of the vertices, as I said, A, B, C, D, and E. That's pretty, easy to understand. And then we have a list of the edges, which are essentially just the nodes, the 2 nodes, which denotes there's a connection between them. So we have a connection between A and B, we have a connection between A and D, we have a connection between B and C, and so on and so forth. So why would we use this and why wouldn't we use this? Let's talk about the time complexity of various, common operations that we'd want to do on a graph. So one of the common operations that people want to be able to do on a graph data structure is, given a node, find all of the adjacent nodes, right? So in plain English, that would be, given a node, let's say in this example, node A, tell me all of its adjacencies, aka what nodes is it connected to? Well, I can tell you it's connected to B and D, right, using my mind. So in this representation, the time complexity to find the adjacent nodes, we're going to code out a solution for how you would, write a function, find adjacent nodes, but we can talk through it in plain English now. You would probably have to loop through the entire edges array, right? And check each one. Is the node that I'm interested in this example, it would be node A. Is it in this connection? Yes. Add that to my list of adjacent nodes. No, skip it, right? So your worst case would be, actually, it's not even your worst case. Every single case, you'd have to loop through all of the connections, right? To check, is my node in this connection? Is my node a part of this pair? Okay, so that is the time complexity to find the adjacent nodes. Another common use case or method that someone might ask you to write when it comes time to dealing with graphs is, tell me if these 2 nodes are connected, right? So given 2 nodes, tell me, is there a connection between them? So this is, again, a big O of E, where E is the number of edges, because you'd always have to check every single edge in the edges list to check, are my 2 nodes connected? Are my 2 nodes connected, right? So this one is a worst case scenario, because you might find that the first edge is your 2 nodes that you're looking for, right? And then you could say, return, great, I found it. Worst case, though, it's the last one. It's the last pair in the edges array. So you'd have to go through all of the edges. So worst case, it's big O of E, where E is all of the edges. Now, another thing we want to talk about is the space complexity. How much space is it going to take up to store this representation of a graph? So as you can see in my little brief code below, you'd always have to store an array with all of the vertices. So you'd at least have to have an array of length number of vertices. And you would also have to store an array in the edges array for every connection, right? So the space complexity has a big O of V plus E, where V is the number of vertices and E is the number of edges, because you'll always have to have at least a list of all of the vertices and at least a list of all of for every single edge. So you add those 2 together, and that's how you get the big O of V plus E. As promised, I'm going to live code some of these different representations of graphs in JavaScript. So I'm just going to be using my Visual Studio Code editor, and I've just made a file called graphs.js if you want to follow along. So remember, we are coding the edges list and the vertices list, right? So as you can remember, I'm sure from the slides, we want to have a vertex list, which is just going to be an array of vertices, right? So if we want to code out the example from the slides, which was that graph with nodes A through E, essentially, and some connections between them. We literally, you just start out with an array, and you can add in the values of the nodes, just like that. And then we can write up our edges list. And the edges list is also just going to be an array. It's going to be an array of pairs, right? Because it's going to be the nodes and the connections between them. So if you look at our graph as an example, we have a connection between nodes A and nodes B. We have a connection between nodes A and nodes D. We have a connection between nodes B and node C, a connection between node C and node D, a connection between nodes C and nodes E, bear with me here, and a connection between nodes D and nodes E. And that should cover all of the connections that we see in our graph. So when we talked about time complexity and space complexity, we had to talk about not only the representation of the graph, right, but the operations you would do onto a graph that was represented in this way in code. So I think the methods that most people talk about when they talk about, measuring different complexities, time complexities of graphs, are going to be these two methods, right? Find adjacent nodes. So that is, given a node, tell me all of the nodes it's connected to, right? And then also the is connected function, right? Which would take in two nodes and return a Boolean, true or false, if those two nodes are actually connected. So let's get started. For find adjacent nodes, we can just write up the function signature to start, right? Find adjacent nodes, so a function, and that takes a node, right? It has to start somewhere. What are the connections of this particular node? So you take in that node, and you can imagine, again, often when I code something, I think of, well, if I look at the problem and solve it in my head, I think that I'm just getting that answer. But of course, what are the sub-steps that my brain is doing without my actually being aware of it? So if you look at the array, the edges array, and you say, okay, I got a node. I want to know what are all of its buddies, right? What are all of its nearest neighbors? You look through the edges and you look for all of the ones with that node, right? So let's say I'm trying to find all of A's neighbors. So I would look for which connections have A in them, right? So that sounds like a loop to me, a loop where you loop through over the edges, right? And you would essentially ask yourself, we can pseudocode this. Loop through edges array. And with each loop, ask yourself, is my node in the connection, right? Is my node in it? If it is, if yes, push the other node in pair into the adjacent nodes array, let's say, right? That we're going to return. So let's take this one, for example. Is A in the connection, A and B? Yes, it is. So push B, right? Don't push A, because A is not connected to A, but push B, right? If no, keep going, right? Keep looping. Is A in this connection? No. Keep going. Okay, so first things first, sounds like we're going to want to return a list, right? A list of the adjacent arrays. So let's say const adjacent nodes equal an array, right? And the idea is we're going to return adjacent nodes at the end of the function, right? Okay, so I think everybody can follow that. And then I think let's just do a loop, right? For let edge of edges. So that's going to make each edge is going to be a pair, right? Let's say, right? And we're going to say, I think, if you're looking for the occurrence of something in a list, right, you basically are going to look for the index of it, right? So I would do something like const, node index equal edge dot index of node, right? Just look for the node in the pair. And if it's there, you'll get a 0 or a 1, right? Depending on where it is. And if it's not there, you'll get a -1. And doing this allows you to keep track of that index, because remember, you'll want the other one, right? You're not going to want the same one. So after you get the index of, I would say if the node index is greater than -1, right? So that means it found it in the connection. I would say that the adjacent node, which is in the edge, right, is going to be the node index. I'm going to do a tertiary, and I'm going to check, is the node index equal to 0? If it is, the adjacent node is going to be 1, right? So it's going to be the edge at 1. It's going to be the other, right? It's not going to be the where it found it. It's going to be the other one. Otherwise, it's the edge at 0. So what that does, because we know that it's always going to be just an array of 2, right? The node and what it's connected to, the other node, we can easily determine without kind of looping over that second array, even though, of course, index of under the hood will loop over that second array, which one to pull off that's the neighbor. So we don't duplicate, we don't return that A is a neighbor of itself, let's say, right? And then we can just push adjacent nodes dot push the adjacent node, right? Which we just found. And I think we're done here. So we can run this, right? Let's say find adjacent nodes for A, and what are we going to expect that we get back? We are going to expect that we get back B and D, right? So let's see. Oh, I didn't save it. Sorry, guys. B and D, great. Let's try for C, and we would expect to get back B, D, and E. B, D, and E, perfect. Now, the other method that you often will want to implement when it comes time to graphs is this isConnected method, which basically is just checking, given two nodes, is there a connection between them? So let's get started with that one, right? So this is going to be const isConnected. It's going to be a function. And this one is going to take two nodes, right? And it's because we're going to check, is there a connection between the two? So we can do node 1 and node 2. And it's going to return a Boolean, right? Whether or not they are connected. Now this is actually pretty easy because you just have to loop through the edges and see, are they both in one of the subarrays, and stop when there is one, right? So I like this for this one because we want to exit early, right? If we find one that fulfills our case, I like the JavaScript sum method because sum will stop as soon as its predicate returns truthy. So I'm going to just return, right? Because we're going to return there. It will return true or false if any of the functions return true. So I'm going to do edges.sum, right? So we can loop over the edges. And again, we're going to kind of borrow from the first one. We're going to say return if edge.index of node 1 is greater than -1, right? If it's there. And edge.index of node 2 is greater than -1, right? If both of those things are true, then we've found the answer. It's connected and we can return. So that's what's called the predicate to this sum function. And as soon as that returns true, the sum will return true and we'll get our answer. And if it never returns true, it will return false. That way we don't have to continue to loop over the edges if we've already found one. So let's see if that works. So let's say we want to see if C and B are connected, and let's check our edges. C and B are connected, so this should return true, so that's great. And now let's see if A and D are connected. Let's see if A and E are connected. False. Okay, great. I think that that does it for this one. So that is the vertices list and edges list implementation, and I hope you guys followed along with that. For our next representation, we're going to talk about the adjacency matrix. The adjacency matrix is a pretty interesting one. It's sometimes hard to wrap your head around at first, but I actually find it once you understand it, it helps me visualize the graph, unlike the edges and vertices list, where it's kind of hard to see the graph in the code. Hopefully you'll know what I mean. An adjacency matrix is essentially, you have a list of your vertices, again, that's the same, but for your connections to represent your edges, you have a two-dimensional array, aka an array of arrays, and each array is actually an array of zeros. And each array has an array length of however many vertices there are. So you'll see this in a second. Here's our graph again. It's the same graph from the implementation earlier. But the adjacency matrix is, again, it has this two-dimensional structure. It has subarrays equaling to the amount of vertices. So you'll see in our adjacency matrix here, we have 5 subarrays nested in the original, holding array. And each column or value in each subarray, also there are that many indices corresponding to the number of nodes on our list. So you can kind of think of it as each subarray representing a node and each index of the subarray representing a node. What that means is that instead of holding the actual vertex values, it's holding zeros and ones. The 0 and 1 indicating whether there's a connection between those two nodes. So in this example, the adjacency matrix at 0, 1, right? So that is the adjacency matrix, its first subarray, and then its second, the 1 index, or the first index, the second element in that first array. You can see there's a 1 there, right? So what that's indicating is that there is a connection between vertex A and vertex B. How do I know that? That first array is holding all of the connections of the node A. And then each corresponding index in that subarray represents the other nodes of the graph. So at adjacency matrix 0, 0, that's A and its connection to itself, A. At 0, 1, that's its connection, A's connection to B. At 0, 2, that's A's connection to C. At 0, 3, that's A's connection to node D. And at 0, 4, that's A's connection to node E. And you can sort of see here that this becomes almost like a visualization of a different sort of visualization of the graph. This has pros and cons, right? The time complexity to find adjacent nodes is big O of V, where V is the number of vertices. Why is that? Well, as you can see, you can just go straight to that node's subarray and then return true where there's a 1, right? Because that means there's a connection. So that's a pretty cheap operation. The time complexity to check if two nodes are connected is even cheaper. That's O of 1. Why is that? because, as I said, you know already where that connection is modeled in this data, right? So if you're checking the connection between A and B, or the 0th and the 1st, right? All you have to go do is check adjacency matrix at 0, 1. If there's a 1 there, return true. If there isn't, return false. Where this gets very expensive, the adjacency matrix, is in space, right? Because you always have to store all of the possible edges, right? Even if there are no edges, you still have to store that as zeros in your adjacency matrix. And your adjacency matrix array will always grow in both directions, right? You'll have to add subarrays for every vertex added, and you'll also have to add zeros for every vertex added, right? To indicate that there's now a new possible connection for every other node in the graph to connect to. So that ends up being the number of vertices squared, right? It grows exponentially because it has to grow in length and also width, if that makes sense. Now, this can get expensive, obviously. So you might want to think about how many connections are there. If there aren't that many connections, this is not the greatest representation for you. If there are a lot of connections, you'll have to store them anyway. So maybe this is a good representation for you. And because the other time complexities are relatively cheap, that might be useful for you. So these are all things to think about and start to think about when you hear interview questions around graphs. You might want to ask your interviewer, what can I expect the data to look like? Because that's going to determine how you model that data in code. Remember when I said that the adjacency matrix kind of is like a visual representation, a different visual representation of the graph? Well, something that's super cool about adjacency matrices is that if they're undirected, which is something we will talk about in the coming slides, the adjacency matrix is actually symmetrical about an axis. So I'll show you what that means. So as you can see, about this axis, the connections line up on either side. Why is that? That is because if there's a connection one way in the graph between two nodes, there's a connection from the other node back to the original node, right? Every connection is two ways. So that is kind of neatly represented in the adjacency matrix, which is something I find super cool. So for this implementation of the graph in code, we're going to be showing how you might model the graph as an adjacency matrix. So we're going to start with, similar to the other representations of the graph in code, we're going to start with an array of vertices, right? So this is going to keep track of what data is in the graph, right? Or what node data is in our graph. So using the same example from before, we have 5 nodes, A, B, C, D, and E. And the difference in this representation is that instead of a list of all of our edges, we're going to have this 2-dimensional array called an adjacency matrix. And each row is going to represent a node, right? Each of these is going to represent a node. And in each row, we're also going to represent that node's relationship to all the other nodes, right? So that's what makes this an expensive space representation, because this 2-dimensional array, this 2-dimensional nested array, grows each time you add a node, both directions, right? And that's the definition of square, right? It's growing v by v in either direction. So I'm going to mark all these as 0 at first, and we'll fill them in together so you can really understand what each spot on this adjacency matrix is representing. So this whole row, this is representing node A, right? This 0th row is representing the 0th node in the vertices array. And each of these zeros is representing A's connection to all the other nodes. So this one is representing node A's connection to node A. Now, for our graph, that's always going to be 0. We don't have any nodes that are connected to themselves. In other graphs, it might be 1 though. You might have what's called a self loop. We'll talk about that in coming slides. What that just means is that there's a connection or an edge between a node and itself. But for us, that will be 0. This is representing node A's connection to node B, which we know there is one. So we're going to put a 1 there. This is node A's connection to node C, which there isn't one, so we'll leave it 0. This is node A's connection to node D, which there is one, we'll make it 1. And this is node A's connection to node E, which there isn't one again, so we'll leave that as 0. So I hope that's a little bit clearer. We'll go through these and fill them out relatively quickly, but this is representing node B's relationship to all the other nodes. So node B to node A, we know there's a connection, so let's put a 1 there. Node B to itself, nope. Node B to C, yes, there is a connection. And then there's no connection between nodes B and D and E. This is node C. It does not have a connection to node A. It does have a connection to node B. It doesn't have a connection to itself, and it's also connected to node D and node E. This row is node D. Node D has a connection to node A. It does not have a connection to node B. It does have a connection to node C. It doesn't have a connection to itself, and it does have a connection to node E. And finally, this is representing node E, which has connections to nodes C and D. So those are those two positions. Now, if you had to write this in code, something to generate a matrix and then a method to add connections, that would be relatively straightforward. All you would do is initialize an adjacency matrix with the number of vertices of subarrays in the matrix and zeros also equaling the number of vertices. And the connection would just take the two nodes and you would find the adjacency matrix at square bracket, the row of one node, and then the column of the second node. And you just put a 1 there. So that would be pretty straightforward. For our examples, we're going to be talking about those two methods, right? Find adjacencies, and is connected. So find adjacencies. Let's talk about that first. How would we do that with our brains? So if you want to find all of the things A is connected to, well, we just filled this out. That's easy, right? You just take the row that represents A and you look for all of the ones in that row. So right here, it's connected to B and D. So what that sounds like to me is getting the row, right? And then just looping through it. And when there's a 1, you look for whatever node is at that index, right? So let's write that out in real code. So let's say const find adjacencies is a function. It's going to take a node, right? And so at this point, the first thing we want to do is we want to get whatever row is represented by this vertex, right? Or whatever we get passed in. So I'm going to make a small structure called vertex indexes. And it's just going to be an object which is essentially going to map the indices to the node values, right? And I'll explain why I'm doing this in a second. But this has to do with keeping our time complexities as they should be, right? We don't want to have to, every single time we get a node, also loop through this array one time to figure out which corresponding subarray matches that in the adjacency matrix. So this is a way to do that just in constant time. When we get a node, we'll immediately know what index it has, and therefore what row matches it in the adjacency matrix. So you'll see why that's important as we code this problem. So the first thing we want to do, right, is we want to keep track of those adjacent nodes. That's going to be, no matter what, we're going to want the adjacent nodes. We're going to want to return the adjacent nodes. And then I think what we'll want to do is, right, get the row in the matrix and then loop through that. And then if there is a 1, push that node. Otherwise, skip. And then I think we should be done. So let's see. We can actually, because we're going to have to be looping through the row, each subarray, or not each subarray. We're going to have to loop through the one subarray that represents that node, right? So we can do a for loop, right? And we can say I equals 0 and I is less than the vertices dot length, right? Because we know that each row is going to be the length of the vertices. Because each row, each value in the row corresponds to all the other vertices. And then we can just check, right? We can just check, and this is where that kind of in between data structure will come in, this vertex indices. We can say, the node vertex equal vertex indices at the node, right? So this is going to give us an index. And then we're going to want to get the row, right? So we're going to say the adjacency matrix at that node vertex. So that is going to, let's say we get A, right? A is 0. So we're going to get this row, right? It's the adjacency matrix at 0. And then we're going to want to find whatever I, right? We're looping through that row. So that is just going to be I, right? So if that is equal to 1, we are going to push that to our adjacent nodes, right? And we can just easily, now that we have that index, right, we can push whatever the vertices array has at that index, right? So if we have found that at I in the subarray, there's a 1, right? This is A. So at that index in this array, that will give us what is represented, right? So that is node A. And I believe that that should do it. So let's run this. Let's write some test cases. So let's console log find adjacencies for A. And we'll expect to get, I believe, B and D, right? B and D, perfect. Let's find the adjacencies for C. We get B, D, and E, and we can even check this ourselves, right? So this is C, and here it has a connection to B, D, and E. And then let's try one more E, and we get C and D as we expect. So that's great. Now, the isConnected function, again, is also very straightforward for the adjacency matrix. So let's get started with our function signature isConnected. And we said this is going to take 2 nodes and return a Boolean, right, if it's actually connected. So we'll get the 2 nodes, and all we'll want to do is get the indices, right, the indices where that is tracked in the adjacency matrix. So we can say const node index 1 is the node, what did I call this? Vertex indices, excuse me. Vertex indices, right, at that node 1. And then node index 2 is going to be the same thing, right? The vertices at node 2. And then we can just, right, we're going to, if you haven't seen this, a double bang just coerces any other value to be an actual truthy or falsy Boolean. We can just check, right, the adjacency matrix at that node index 1. And then that will represent the subarray. And then at the node index 2, that will represent whether there's a connection there or not. So that's going to return a 1 or a 0, and that double bang is just going to coerce that into 1 being truthy and 0 being falsy. So let's see if that does it. Is connected. So A and E are not connected, I believe. So that's good. A and B are connected, so let's see. That's great. And then let's see B and C. That is connected as well. Let's do one more. B and E, not connected. Perfect. So as you can see, those are our two methods for finding the adjacencies and whether two nodes are connected using an adjacency matrix. And finally, we're going to talk about our third implementation, which is the adjacency list. The adjacency list is pretty common, I think, probably because the time complexities of both of those very common methods and the space complexity are all pretty decent. So let's take another look at that same graph that we've been using. The adjacency list essentially stores a list of vertices, like all the other examples, and then it stores a list of adjacency lists, which are essentially, for each node, list all of its adjacencies, all of the nodes that it has as its closest neighbor. So that's pretty straightforward. The time complexity to find adjacent nodes will be O of 1, because you can just simply look that up and return the value at that index in the adjacency lists array. So for example here, if I wanted to get all of B's closest neighbors, I would just get the list for B of B's closest neighbors. That's pretty straightforward, which as you can see at index 1 will be A and C. The time complexity to check if two nodes are connected are O of log V if each adjacent row is sorted. So essentially, to look for whether or not two nodes are connected, you can just look at the subarray at that index and then look for the other node in that index. Now, if they are sorted, meaning if the nodes are sorted in some greatest to least, least to greatest sort of way, a regular looking up something in a sorted array will be log V, which is excellent for our time complexity. For space complexity, it is big O of E, where E is the number of edges. You will always only have as many things in the subarray as there are edges, right? Every item in a subarray represents one edge. So that's how that array will grow with the graph's edges. For this live implementation, I'm going to do something slightly different. I'm going to make the node and the graph each their own class so they can kind of manage themselves and the connections between them. So if you remember, we're using the implementation of an adjacency list, right? So we're going to need a class of type node, right? And we are going to also need a class of type graph. Now, the graph will be the thing that kind of holds what nodes are in it, and the nodes are going to each know their own value, and also, if you remember from the slides, they will store a list of edges that are connected to it. So we can easily initialize the node with a constructor, and that can take a value, right? So that will be the node's value. And we can set this dot value equal to that value. And then we can also set an edges list, and that will just be an empty array at first, right? So I hope that makes sense to everyone. It's pretty straightforward. And then moving on to our graph, I think for our graph, all we'll really need to initialize it with is nodes. So we can take in some nodes into its constructor, and we can create a this.nodes, which will be all of the nodes that get passed in. when this graph is initialized. Now, if you're not familiar with the ES6 spread operator, all I'm doing here is it's shorthand for pushing each individual node that gets passed in the nodes array into the new array, which will be the graph's this.nodes. And yeah, so that should be pretty clear for everyone, not complicated at all. And what that means is if we're going to implement that graph that's from the slides, we're going to have to do some initialization. So I think we're going to want to make a node A, right? So that will just be as simple as saying new node A. And we can do that for each node in the graph, right? So this will be node B, node C, node D, and node E, all accordingly. So we're just setting ourselves up here to be able to create a graph, right? So we can do const graph equals new graph. And you'll remember our constructor takes in an array of nodes, right? So we can just go ahead and pass it node A, node B, node C, node D, and node E. And if we log out what that graph looks like, first of all, let's log out a node. Right? We can label that so we know what we're seeing in our console. And let's see what we get here. All right, so it looks like for our node A, we get a node with a value of A and an edges list that's empty. That's great. So as you can see, we have a graph with nodes in it, and those nodes are all of those nodes that we passed in our constructor here, right? And they all have empty edges lists because they're not connected to anything. Okay, so we should probably make a method to connect those nodes if we so choose. You know, just to be totally thorough, we can also make an add to graph function, just in case we want to add a node after we've initialized the graph. And this is as simple as just pushing that node to that nodes list, right? That's all we have to do to add it to this graph, which is pretty sweet. Okay, so connections. So let's say connect, right? So I think we'll want to take a node, right? Because this is going to be an instance method. So we can use this to refer to this nodes that's, you know, doing the calling. And all we have to do is push that node to the edges list of the node that's calling, right? So what this will do, let's say, if we say something along the lines of, you know, node A, right? We're going to want to set up that graph from the slides. So we're going to want to say node A dot connect node B. And what that will just do is it will push node B into node A's edges list. Now, we'll also want to show that there is a connection from node B back to node A, right? This is in an undirected graph where every connection goes both ways. So if node A is connected to node B is also connected to node A. This is not always the case, of course. Sometimes there is only a connection one direction between one node and another, but we'll talk more about that in the slides. For now, this is going to be a two-way connection. So all we have to do is also push this node, right, into the, oops, I keep forgetting my pushes, into the node that we called this function with into its edges list. Okay, so that should take care of that, and we can start building our graph. So there is a connection between node A and node B, right? We've already determined that. There's a connection between node A and node D. There's a connection between node B and node C. There is a connection between node C and node D. There's a connection between node C and node E. And finally, there's a connection between node D and node E. So that should take care of that. And I think we can, kind of go through all of these to see what we have so far. So let's get rid of these console logs. And let's loop through them. Let's print out all of our, let's visualize our graph here. So let's make a for loop where we're just going to loop over those nodes of our graph. And I think for each, I am going to print out node dot value. So that should show each node in the graph, right? And then I also want to loop over those edges, right? So let connected node, right, of node.edges list. So for each node, we're going to print out each of its connections, aka its edges. And we can write some sort of log, like let's do node and this way we can see each node and what it's connected to. Let's run that and see what we get. Okay, so let's see. We have node A, and node A, as per our drawing, is connected to nodes B and D. That's great. We have node B, and node B is connected to A, right, because it goes two directions, and it's also connected to C. Node C is connected to a lot of nodes. It's connected to B, D, and E. That's all accurate. Node D is connected to A, C, and E, also accurate. And node E is connected to C and D. So that's also accurate. Okay, great. So our graph implementation is working so far. So now we can move into the kind of, the meat of this implementation, which again are those methods, get adjacent nodes and is connected. So I'm going to put those on the node class, because in my mind, those are methods that have to do with a node understanding its own state, because in this implementation, the node is keeping track of its own edges, right? So we can say get adjacent nodes. And let's talk this through first, pseudocode it as we usually do. To get an adjacent nodes, it's very easy for this one, right? We can just return its edges list. Super easy. So that's not pseudocode, that's real code, right? So I think I'm just going to return this .edges list. And, I might map this to be each edge's, value rather than just the node, right? Because this is going to be an array of nodes. That way you could theoretically do operations on each of those nodes rather than just have that value. But I think for now, I'm just going to map it to values just so you guys can see kind of what we're getting back here. All right, so let's log out node A dot get adjacent nodes. Let's see what we get here. We should get A and D. B and D, excuse me. So we're also still logging all of this out, so we can get rid of that just so you guys can see. So we get B and D. Excellent. Let's do node C just to make sure that works. Perfect. B, D, and E. Exactly what we anticipated it being. And, is connected is really pretty similarly easy, right? All we're going to do is check if the node that gets passed in is in this node's list, right? So we can just return, right, this dot edges list. We can map that to the edge dot value. And then we can check if the index of that node is greater than -1, right? That's going to be that node's value, of course. Now, of course, that's not free, right? To map all of the edges to their values, this is also not correct. Sorry, guys. To map all of the edges to their values and then to use the index of to look for that node's value, that is not free. And, depending on the interview question, you're going to want to talk through all of this with your interviewer. But to show you how this works, I'm just doing this pretty simply and pretty straightforward. And with graphs, it depends on what the interviewer is asking. So that's just something to keep in mind. Don't think that this is free, that I'm using these built-in methods of the language. So let's say is connected. That sounds better to me. And let's see, let's console.log if node A is connected to node B, which should be true. And that is true, right? Let's see if it's connected to node C. That should be false. Great. Now let's see if D is connected to C. That should be true, I think. And let's try one more. Let's say D is connected to A. That should also be true. And there you have it. That's a simple, straightforward implementation of an adjacency list for graphs. Hope you enjoyed those implementations of the graph data structure and code. For our next segment of this video, we're going to be talking about some more graph terminology you may hear whenever someone talks about a graph. So I mentioned this when we were working on the implementations of graphs, but there's this concept of directed versus undirected graphs. Undirected graphs mean that the connection is both ways, aka node A is connected to node B, and node B is connected to node A just as much. A good example of an undirected graph is the Facebook graph, where in the Facebook world, users are nodes and friendships between the nodes are the edges or the connections between them. Of course, if you accept someone's friend request, you are as much friends with the other person as the other person is friends with you. There's no such thing as a one direction friendship in the Facebook graph. There may be many ways two users are connected on Facebook, though, which is why the graph is so powerful, right? As opposed to a tree, there might be many different paths for you and someone else on Facebook to be friends. Directed graphs, however, there is a direction between the nodes, meaning from, let's say, city A connected to city B, there is only one direction you can go. You can only go from city A to city B. To go back to city A from B, you might have to take another route. The internet can be modeled as a directed graph, where the individual web pages in the internet are the nodes, and the links between the pages are the connections. It's directed because just because one web page has a link to another web page does not mean that that other web page links back to the original page, right? That is a one direction of data flow, and that has to be modeled in the graph as such. The degree of a node is the number of edges connected to the node. So in a directed graph, a node can have an in degree and an out degree, right? Because it's going to have a certain number of connections that point to it and a certain number of connections that it points to, right? Because there's this concept of direction in the edges. So there's, an example of how the internet as a graph could look. Another concept that we haven't talked about yet is weighted versus unweighted graphs. A weighted graph is a graph in which the edges have values corresponding to weights. A good example of this might be a city, right, or an intercity road network, where between the different cities, there are roads that each have lengths. So one connection from city A to city B will not equal the same distance from, as a similar connection that's from node, city B to city C. There's going to be different lengths to those roads and therefore different weights in the graph. An unweighted graph has no weights to its edges, so every edge is the same as any other edge. So far, all of the graphs that we've been using have been unweighted, right? Every edge is the same as any other edge. But for those implementations, we can talk about how you could store those weights. Let's say for an adjacency matrix, right? That's that two-dimensional array of zeros. Instead of storing ones or zeros, you can store zeros and weights, or dashes and weights, let's say, right? Where each number on the adjacency matrix is the weight of that connection. For the vertices list and edges list, you can just add a third member of the array representing an edge for the weight of that edge. And for adjacency lists, instead of storing just lists of the node values that you're connected to as a node, you can store objects, right? And each object can have a value and a weight. It can be an array of objects instead of an array of just values. You may have also heard of cyclic versus acyclic graphs. This is another pretty easy concept. In a cyclic graph, there is at least one cycle, meaning there is at least a path from one node back to itself, right? There has to be one kind of loop in the graph. Acyclic graphs, however, mean there are no loops in the cycles, meaning no node can ever be traversed back to itself. Both of these graphs can be directed or undirected. Directed acyclic graphs, otherwise known as DAGs, have applications in computer science and can often be used to represent a complex data processing flow. So here's an example of a cyclic graph, right? You can go from node C right back to itself. This is a directed cyclic graph. And then here is an example of a directed acyclic graph, or otherwise known as just a, something you might have seen at work, right? This is just a complex data processing flow where data comes in from one direction and it leaves modified or changed in another direction. It can be changed in different ways depending on different corresponding parameters, depending on your use case, but there's no way that that data is going back over a previous step again. So that is a directed acyclic graph. Now, when we were talking about implementations, we talked about how in an adjacency matrix, if there are a lot of edges or a lot of connections, it might be useful to store it as an adjacency matrix because you have to store those edges anyway. However, if there aren't that many edges, it might be more useful to store it as an adjacency list. Another way of saying whether a graph has a lot of edges or connections between the nodes is saying a graph is dense or sparse. A dense graph being one where there is a close to the maximum number of edges that a graph could possibly have, and a sparse graph being that the number of connections are close to the nodes in the graph, right? There is the least possible amount of connections can be the number of nodes, right? Minus one, of course. It's one connection between basically a line, right? One connection between every node and no other connections, right? It's just the bare minimum to get all those nodes connected to form a graph. Another good tidbit to know about graphs is that there is such a thing as a self loop, meaning that there is a connection between a node and itself, which is just, indicated by just a loop back to itself. This is like a web page linking to itself would be a good example of that. And multi-edge graphs are when there are multiple edges between two vertices. So a good example of this might be, again, that inner city graph of the nodes as cities and the connections as roads between the nodes, there might be different roads between city A and city B, maybe with different lengths. And so there might be multiple connections between those two same nodes. Another good term to know when it comes to talking about the graph data structure is a simple versus a complex graph, right? A simple graph is a graph that has no self loops and no multi-edges. So in all of our other examples, those have all been simple graphs. There have been no nodes connecting to themselves and no multiple connections between nodes, just the one if there is one. In a simple directed graph, the maximum number of edges will be equal to n times n minus 1, where n is the number of nodes. So this is the maximum amount of edges that can possibly exist on a simple directed graph. So if you think about this for a second, in a directed graph, the maximum amount of edges between two nodes will be 2, right? Going from point A to point B and then point B to point A, right? So the maximum number of edges will be equal to n minus 1, right? N minus 1 is the minimum number of edges that you have to have all the nodes connected, times n, right? So because every node might be connected to every other node. In a simple undirected graph, it's the same thing, but you divide by 2, right? Because that direction is it's always going to be two-way. Therefore, it's always going to just count as 1 instead of 2. So that's how you get that over 2 piece of that. So in our next videos, we're going to talk about all the traversals that come with graphs, along with some specific interview questions. Some of the most common graph interview questions are things like find the shortest path between two nodes. I think we've all, heard about that sort of question. Check if an undirected graph contains a cycle. So this would involve traversing a graph and looking for that cycle, again, that a path from a node back to itself. Or given an undirected graph with a maximum degree D, find a graph coloring using at most D plus 1 colors. So coloring is another thing that we'll talk about when it comes to graph interview questions. And there are a lot of different ways you can color a graph based on certain parameters. So we'll go through all of that in the coming videos. And again, here's an example of an inner city, a weighted graph. It looks like it's undirected in this case, and someone might ask you to find the shortest path between city A and city D, for example. And there's that traveling salesman that we all have come to love. So to recap, today we talked about all sorts of graph terminology, and in addition, we went over some implementation examples. So we learned about weighted and unweighted graphs. We learned about cyclic and acyclic graphs. We learned about adjacency lists, adjacency matrices. Tell me in the comments below, I don't know. We learned about all of the different ways in which you can actually have nodes connected by edges, there's a lot of different ways. In the coming videos, you can get excited for all about traversals, right? Once you have this very powerful data structure that there are many different ways to model data with, how do you go over it, right? Like how do you loop through it? How do you find those paths? All of that sort of thing. And we're finally, in the videos after that, going to be talking about real world interview problems where you're going to need to use all of your knowledge about graphs to find solutions. So look forward to that and get excited for more CoderByte content. Thank you.